Chip just gave us a nice overview of lunar magnetism and what we can learn from this core. I'm going to speak about samples from the same core, but focus more on the Apollo 17 site. The Apollo 17 lunar module landed in the Taurus-Littrow Valley on the basaltic floor of the Taurus-Littrow Valley between the North Massif Mountains and the South Massif Mountains. And this carefully selected site gave us the opportunity to explore this landslide deposit. And here in the simplified map, the basaltic floor is shown in dark gray, the highland lithologies are in white, and the landslide deposit is off-white. And this deposit gave us the opportunity to possibly sample lithologies from higher up on the South Massif, and also offered the possibility of exploring the effects of a landslide activity on possibly mobilizing volatiles. Here's what the site looks like from the LROC camera from orbit. So here's the South Massif Mountain here. Again, you see the lighter color. And the X marks the spot of the approximate sampling location of the 73001-002 drive tube. And visiting this landslide deposit was a primary objective of the Apollo 17 mission. And as Chip just showed, from this deposit, we found some very rare granitic lithologies. And I'm going to focus on the basaltic lithologies that we found. Oops. So the Apollo 17 soils, like most lunar soils, especially ones from highland Mare contacts like the Apollo 17 site, contain mixtures of both Mare and highland components. And here I'll be focusing on Mare basalt fragments we found in the 1 millimeter to 150 millimeter, 150 micron fraction of 73002. That's just the upper part of that double drive tube. We examined polished grain mounts of 3 size fractions from 7 depth intervals, covering the whole length of that section from the lunar surface down to 18 centimeters. We looked at a total of 1,425 particles, and we found 58 basalt fragments with a variety of textures that I'll show in a few minutes. For comparison, there are about 80 individually numbered hand-sampled basalts from the whole Apollo 17 collection. So you can find quite a few, much more material, a variety of material by looking at smaller, larger like soil samples, rather than just looking at hand-sampled soils, hand-sampled samples. Oh, got it. So here's a little overview of the Apollo 17 basalt suite. Most are classified as high titanium. That means that they're rich in ilmenite and iron titanium oxide. And they fall into 3 main groups based on petrographic observations. Some have quenched textures. Most are medium to coarse grained. Some are olivine poor. Some are medium grained and also olivine poor. But on the other hand, they can also be classified on the basis of trace element systematics. And they are classified into multiple groups based on trace element contents and ratios, as shown here in this plot after Neal and Shear et al. This shows a terbium versus lanthanum plot, and there are several distinct groups. But in addition to the high TI basalts, there's also a rare VLT basalt group, a very low titanium basalt that was found several years after the Apollo 17 mission. And they are rare, and they're found as small fragments in soils and breccias. And it was first found in the Apollo 17 deep drill core. So for this study, we can start grouping our 58 samples in terms of texture and mineralogy. And so the criteria we can use is grain size, so some coarse versus fine grained. Are they ilmenite rich, ilmenite poor, olivine bearing, olivine free, and free silica bearing versus silica free. Again, we have small fragments. We just have to assume that they're representative and just classify what we see. And we find that most samples are in the high titanium, they're ilmenite rich, and they're medium to coarse grain, not quenched textured, like this one. So this is a backscattered electron image. In this type of imaging, the mineral grains, the albedo of a mineral grain is directly proportional to its average atomic weight. So epoxy is black, silicates are various shades of light gray to dark gray, and the heavier iron titanium oxides, metals, and sulfides are very bright. So here we see ilmenite grains with some dark cores enclosed in olivine. These dark cores are actually malcolite. They're darker because they have a higher titanium to iron ratio than ilmenite. And this mineral was first found among the Apollo 11 samples, and it's named for the 3 Apollo 11 astronauts, Armstrong, Aldrin, and Collins. Here's a more typical looking basalt with a modest amount of ilmenite, plagioclase slabs, and some coarse, fairly iron-rich clinopyroxene. And the next few images, the plots on the right will show the pyroxene compositions in the sample and possibly comparable previously reported pyroxene compositions by Neal et al. So this shows that this basalt is rich in fairly iron-rich and calcium-rich pyroxene. You don't find orthopyroxene or very calcium-poor pyroxene in Mare basalts. In contrast, here's a sample with much coarser ilmenite, quite a contrast from the first sample I showed. A very coarse, blocky ilmenite grain here, and some clinopyroxene, again with calcium-rich pyroxene, trending down towards more calcium-poor and iron-rich compositions, possibly mimicking this trend. If this is a type 2 basalt, this might be a fairly rare type. Of the 26 samples Neal et al. Studied, only one was a type 2. We can also find needle-shaped grains, like in the first sample I showed, and occurring with blocky grains. And again, we have commonly seen subcalcic pyroxene and very iron-rich compositions. As I mentioned earlier, silica is sometimes found. It's a late stage phase occurring, crystallizing after plagioclase and pyroxene. And we did find a very good candidate for one of those rare VLT basalts. You can see here, this is very low in ilmenite, just a little bit up in here. And this bright grain here is both ilmenite and iron sulfide. But the particle is mostly clinopyroxene and plagioclase. The pyroxene is onto some very iron-rich compositions, and we think this field of pyroxene compositions mimics the previously reported field for VLT basalt. So this is a good candidate for a VLT basalt. Plotting all our analyses together for including some samples I didn't show, the field of pyroxene compositions that we see is similar to the previously reported field. So we may have all 3 types represented, but we can't be sure of that because we don't have the bulk compositions. So despite the similarity to the previously reported field, the presence of new basalt types cannot be ruled out. And Neal showed that the trace element contents and ratios in Apollo 17 basalts probably reflect some mantle heterogeneity lunar mantle heterogeneity beneath the Apollo 17 site, but the magmas after eruption followed similar evolutionary paths, basically pyroxene fractional crystallization, giving you similar crystallization trends and similar pyroxene compositions. So what are our next steps? Well, first we should obtain bulk major, minor, and trace element analyses of additional Mare basalt fragments to enable that for a more robust classification and a search for new types. Also, we can do age dating, stable isotope analyses, especially of these new types, to improve our understanding of the lunar evolution of the lunar magma, lunar mantle, and its composition and variation through time. We also have samples from 73001 to look forward to. It was recently extruded from its originally sampling tube this past March. It's twice as long as 73002, so twice as much material. Samples are just now becoming available to the preliminary examination team, and taken together, this double drive tube will provide a 50-centimeter record of both the local stratigraphy and these cores provide a record of solar activity spanning millions and millions of years. You can look at the record of solar wind implantation, for example, and look at the abundance and isotopic variation over time. And as a concluding statement, I would say from these initial results for 73002 that were being presented here this morning and at the last two LPSCs, plus the knowledge to be gained from studying the entire double drive tube, it's clear that soil cores are a valuable component of any lunar exploration and sampling program. Thank you.